Hello everyone, we're back again. We're going to continue to look at assembly language and to understand a little bit more the details of the language and the process of writing it and some of the syntax. So let's start again by talking about what the process of writing instructions for specifically the NIOS 2 processor and how we can do that via assembly language. Okay, so as you will see in the lab, if you haven't already examined the first introductory lab, you soon will, and you'll note that the assembly language is written purely as a text file. It can be written in any text editor, and it contains a list of the assembly language statements. Okay. We should also recognize that our assembly language listing is contained in a text file that has a .s extension. Okay, and again, you will, if you have your operating system enabled to show your extensions, you'll note that the files that were made available for the lab have a .s extension. From there, in order to generate the instructions that the CPU understands, in assembly code goes through a software package called an assembler, as mentioned before, and this assembler translates these assembly language commands into binary instructions, or binary machine language, or binary code, and this is executable code that the processor is able to interpret and execute. Okay, some of you may be already asking yourself, if you start to look into assembly language, why would we use assembly language rather than a higher level language? And you might be interested to know that even when writing in maybe C or C++, when writing an application for a processor, before that application is deployed to the processor, it actually goes through and is compiled first into assembly language, and then it goes through assembly language specific to that processor, and then it is assembled through an assembler to create those binary instructions. So we've just gone one step closer to the binary instructions, and we want to use that in this course because there's a direct one-to-one link between the binary instructions and the specific assembly language instruction, which makes it very clear what is happening at the processor level, down at the hardware level, when these instructions are being executed. Okay, so let's imagine a file that has the following source code in it. Okay, so very simple. Let's just, for this example, use an instruction that we've already kind of investigated, and add immediate instruction where we add a value of 1 to R5 and store the result in R5. So this is really an increment the value in R5 by 1. Okay, and let's do this again, just for an example. Let's do this 3 times. Okay, so we've just incremented the value in R5 3 times by 1. Okay, if we take this source code and run it through an assembler, it's going to generate the binary instructions that need to be programmed into the memory of the processor that it will then execute. And so we are working in a simulator and on a virtual processor for this course currently, but we can still see what is happening at the machine code level. If you look at once you compile and load your program onto the simulator, the CPU later that we're using for the labs, you'll notice that in the disassembly listing that there is a listing of the actual binary instructions. So if you click on the disassembly tab, which walks you through in the lab. One thing I'll point out about that disassembly tab in the online simulator is that they show the address, which we're going to look at here in a second, and a column that shows the instruction that's at that address and then shows the actual assembly listing. They call the instruction an opcode, which is not technically correct. We know that the opcode is just a subset of the instruction. Right? If we looked back on the previous lecture, the actual opcode is said is just one part of the instruction. The entire binary instruction provides not only the opcode but also your source and destination locations. So that column labeled opcode is not technically correct. It should be called binary instruction or instruction word or something like that. Okay, but let's move on. So if we put this source code through an assembler, and I'm going to kind of show address. I'm going to show a column that's contents at that address. So this would be, maybe I'll put it below here. This is the well, let's just call it binary instruction. And I'll put a column for the associated source code, much like what is shown in the simulator and is shown in many tools when you actually have the code loaded on to your processor. The address here, I should also maybe point out, this is the address where the instruction is located. Okay, so the corresponding instructions for, so maybe I'll fill in the source code first from up above. So the associated source code that will be generated from the assembler is the or the associated contents or binary instruction is going to be generated from the source code that's shown up above, which is this add immediate instruction that's listed 3 times. Okay, so this is the source code. Okay, and each of those instructions, so if these are the only 3 instructions that are in our program, in our text file that makes up our program, those instructions are going to by default start at address 0. Okay, and so maybe I'll just put a disclaimer here to say by default the NIOS 2 starts at address 0. Okay, and if we were something else probably worth noting here is also looking at the simulator, these values that are listed here are in hex. Okay, and the contents I'm going to list, the binary instruction I'm going to list is also in hex. So if we went back, and you can go back to the last lecture and look at the 32 bits associated with an add immediate instruction and generate that for a immediate value of 1, a source register of 5, and a destination register of 5. And if you take that value and convert it to hex, you'll get an instruction word, or a binary instruction word, that is 294000044, and this is also in hex. Okay, and again, looking at the online simulator, the column that is incorrectly labeled as opcode, which is your binary instruction, is also listed in hex. Okay, so that's what is going to be generated for the processor when the source code is assembled, and at least for the first instruction. Okay, so it tells us where the address of the instruction is and what the specific binary instruction is at that address. So at address 0 in memory, it's going to insert this specific binary instruction. Okay, so the binary instruction for all 3 of these is going to be the same because all of these instructions were the same. So the instruction is going to be the same for all 3 lines of this simple program. Oops. 2940044. So that's a increment register 5 by 1 instruction. But where are each of the instructions going to be located? Well, each instruction takes up 32 bits. They're 32-bit instructions, but the NIOS 2 processor can address down to a single byte of memory. So therefore, since each address or each instruction takes 4 addressable spaces, the address of each consecutive instruction will be 4 addresses later. Okay, so this first instruction, I'll just highlight it again. This first instruction is going to take up address 0, 1, 2, and 3. The next address will take up address 4, 5, 6, and 7. And then the final instruction will start at address 8. And again, these values are all in hex. So just put a note about this as well, that the NIOS 2 can uniquely address. This is an important note. This is going to come up in some future discussions as well, but the NIOS 2 can uniquely address a single byte of memory. And each is 4 bytes, or 32 bits, if you want to think about it in bits. Okay, therefore the address increases by 4 for each instruction. Okay, and maybe I'll show that arrow where we see each of the instructions is at an address that's 4 addresses later than the previous instruction. Let's talk about another very useful feature of writing in assembly that will really make your code much more readable and make redirecting your code much simpler. And that's labels, or sometimes referred to as address labels. Okay, so this is probably best served with an example. So let's show some source code written with the use of labels. And you will have or will soon encounter labels used in the code written for the lab. Okay, so I'm just going to use very generic labels, label A, and then put in assembly language instruction, label B, and put in the assembly language instruction. I'm going to use the same simple example that we just used. Okay, so we're incrementing the value in register 5 3 times. Okay, now again, if we take this source code and run it through our assembler, it will generate our binary machine language. Okay, and now that generated language will have labels associated with each address. Okay, so we'll end up with generated code that looks like this. So I'm going to use my same columns that I used up above. Okay, so my first instruction was at address 0. The instruction, as we said previously, was 294000044. If you go through the work of converting a add 1 to register 5 and store the result in register 5, you should be able to convince yourself that that instruction is correct. And let me take this instruction and let's just copy it 3 times here. Okay, so there's the 3 instructions. Of course, they're at address 0, 4, and 8 in hex, but now each instruction, or the address of each instruction, has a label associated with it. Okay, so what's the value of that? Well, each label, if each label is associated with an address, then we can use those labels as a convenient means of referring to an address. Okay, So maybe up here I should have labeled this column the label. Okay, so my labels are, in this example, they can be kind of whatever text label is meaningful or you find meaningful in your application. In this case we use very generic label A, B, and C, and each of those labels has a value associated with it, which is that of the value of the address of the instruction which it referred to. Okay, and this value, the value associated with this label, note that I didn't have to know the address up here when I wrote the instruction. I just the address of where that instruction is going to be, I just give it a label. The beauty of this is later in my code I can make reference to that label without ever having to worry about the specific location of that instruction, the specific address location of that instruction, because I can refer to it generically through its address label. Okay, so the label value gets generated when the program is assembled, and it's constant and cannot change during program execution. Okay, so let's look at a simple example of using a label. And let me grab this code above here, and let's use this code to show an example of the use of labels. Okay, so my code started out with these three instructions, but I'm going to add an additional instruction. I'm just going to show it over here in the source code. So imagine I had a branch instruction that's specified to branch to label A. Okay, and if we go and look at the branch instruction and figure out what its binary machine language equivalent is for a branch to label A, and again it specifically gets associated with the address of label A, but we don't have to think about this when we write the code. So it would generate, the assembler would generate an instruction that looks like this. And we'll come back to talk about why that is here in a second. This added instruction is going to be at 4 bytes later. We are at address 8 in hex. The next address in hex would be, well, this instruction here is at address 8, 9, A, and B. So then this address, or the address of this branch instruction, is going to be at address C. Okay, I'm going to put in a offset column here, and this offset column is going to refer to the offset with respect to the branch instruction. Okay, and in fact I'm going to add one more instruction here. So if we had another instruction, so the branch instruction, this instruction takes up address C, D, E, and F. So my next instruction would be at 10 in hex, and let's not worry about that instruction, but let's just refer to this as the address of the next instruction after the branch. Okay? So what happens when the branch instruction is executed is it needs to adjust the program counter. So the program counter is that thing that keeps track of where my next instruction is going to come from for the CPU. Okay, so let's just put this here. So the program counter you can see in the simulator window that the program counter is listed under the register window. You can see what the current value of the program counter is. You'll always note that it's pointing to the next instruction to be executed. So that program counter gets incremented to the address of the next instruction okay, so you can imagine this as the program counter gets equal to whatever the program counter value was plus 4. But this happens when an instruction is fetched, but before that instruction is executed. Okay, we'll come back and think about what the meaning of this is here in a second. We haven't talked about fetch and execute yet, but just a little bit of a preview. When a processor is executing instructions, it goes through this repetitive process where it goes and fetches an instruction from the memory location designated by the program counter, or the memory location that's specified by the program counter, and then it executes that instruction, and then it fetches an instruction and it executes the instruction. Okay, just does that continuously with every cycle of the CPU. Okay. So let's think about this statement a little bit more. Okay, so this branch instruction, when this branch instruction is fetched, okay, the branch instruction's fetched, but the program counter gets incremented as soon as that branch instruction is fetched. Before it's executed, the program counter will already be pointing to the address of the next instruction. Okay, so when the this branch instruction is actually executed, the program counter will already be pointing to this address. So that means that when the branch instruction is generated, when the binary machine instruction is generated, it has to be generated to account for the current location of the program counter, the current address stored in the program counter. Okay, so let's look in a bit more detail about what this branch instruction looks like. Okay, so a branch instruction, I'm going to squeeze it in here. A branch instruction is an I-type instruction. Okay, we'll remember that an I-type instruction, we specify the immediate value, the opcode, the other operand, so immediate value and the register that contains the other operand, and the destination. Okay, so this is an I-type instruction which has register A, register B, an immediate 16 value, and an opcode. In our case, we want to specify an opcode that's associated with a branch. We don't actually need to specify any registers because there's no registers associated with this instruction, so they can stay as zeros. But now the question is, what is the immediate value that we have to provide the branch instruction? Okay, so actually let me reverse these. This can just specify register 0, and the immediate 16 value contains the offset that gets added to, okay, this value that gets put in here is the offset that will be added to the program counter. So offset to be added to the program counter when that branch instruction is executed. Okay, so let's look at what the offset has to be in this particular case. Well, remembering that when the branch instruction is executed, we are already sitting at this instruction. Just let me highlight it again to right, we're already sitting at the address of the next instruction, so let's set that offset as 0. The location right before that, we would be off at an address offset by -4, -8, -12. So this is the number of addresses of offset from where the program counter is pointing when the branch instruction is executed. Okay. So based on that, when the branch to label A, because that's where we're trying to go, instruction is executed, the branch instruction that's generated, the binary machine language instruction that's generated, should be generating a instruction with an immediate value of -16. If this were base 10, -16 in hexadecimal is FFF0. Okay, we'll address how to generate signed numbers later, but this would be a 2's complement value. Okay, so this is what the assembler generates in processing that branch to label A instruction. Okay, and if we convert this to the individual bits, these registers are just all zeros, we don't need them. A value of FFF0 is 1111, 1111, 1111, 0000, and the opcode associated with a branch is 0001110, or 06 in hex. Okay, so again, lots of stuff going on behind the scenes as the assembler generates the code that makes use of this branch to label A. Okay, and the beauty of this is that this was done without us ever having to explicitly think about the address and what offset needs to be generated for the executable, the binary machine code. Okay, that all gets handled by the assembler, and all we have to do is is use these labels to refer to the address of a instruction of interest. Let's talk about a few more aspects of assembly language that will be valuable. These are discussed in the lab as well, but we'll cover them here again just to highlight them. As you've seen, I've stated that comments are required in your code that's written in the labs, and it should be included in any code that you're writing. So how do we place comments in assembly language? Fairly straightforward. The pound symbol, or what you guys know as a hashtag symbol, at the beginning of any line indicates that the text that follows that pound symbol is a comment. So that's at the beginning of a comment line. If we want to comment multiple lines of text, which is often useful, we can use /**, put in our comments, maybe set however many lines of comments you want, and we can end the comment by putting another asterisk and /. Okay, so that's commenting. Make sure you comment your code effectively and put comments that are meaningful. Okay, again, the first lab has some guidelines and examples that you'll find useful. Some other things that will be important and necessary as you write your assembly language code is to understand assembly directives. Okay, so what are assembly directives? These are instructions that serve to guide, I shouldn't say instructions, maybe we should say guidance for the assembler program during the assembly process. So it does not generate executable code. Okay, so let's stress that. These directives do not generate executable instructions, so they're not going to be executed by the processor. In our case, the NIOS 2 processor will not be executing these directives. The directives are simply there to guide the assembler process, and you'll see when we look at some examples here in a second. They're distinguished from other parts of the program because directives begin with a dot. Okay, so let's look at a few examples of useful directives. .end is what it sounds. It can be used to indicate the end of a program. So sometimes this is helpful when you're debugging. You've written a lot. You just added a bunch of code. Maybe the program stopped working and you want to start removing some of the lines of code. You can put a .end directive in your assembly language code, and the code will not pass that. Any assembly language instructions past that .end will not be assembled into binary machine language instructions. Okay, so any lines found after this .end directive would be ignored. Okay. Another useful directive is the equate directive. those of you that have programmed in C will liken this to a define statement. So it allows code to be clarified by using text in the place of constants. And you will see that in the examples that appear in the lab manual that it's good convention to use, whether it's a define statement in C or whether it's an equate statement here in assembly, it's often preferred to use text that's in all caps. It'll make it clear to you and anybody else that this text represents a constant value. This allows you to use that text throughout your code in place of the constant value that it is equated to or equivalent to. And when the assembler assembles the code, the text is replaced with the constant value. Okay, so it makes for more readable code and code that someone else can pick up and maybe make sense of a little bit more quickly. Okay, a couple of simple examples. We might use an equate statement to make the text string switches equal to the address of our switches in our processor. Like in our emulator, our switches are at address, actually, sorry, they're at address 1000040. So rather than having to remember that every time I want to refer to the address of the switches, I can now use the text statement switches. Okay, I could even equate a value to a actual instruction. So up above that we saw that the machine language associated with, and I should put the 0x in front of this to make sure it's interpreted as hex. Okay, the hex equivalent of the increment value in register 5 we said was 294000044. Maybe I want to equate that to a text value of increment 5. Another directive that you may find useful, and you will notice it's been used in the lab, is the .org directive. This directive tells the assembler to begin placing binary values at consecutive memory locations starting at the address given by the directive. So let me just write that out. So it tells the assembler to begin placing binary values at consecutive memory locations starting at the address value given with the directive. It's a simple example of this. I'll show, let's say I do a .org 0x2000, and any assembler or any, whether it's data or any assembly language instructions that occur after this .org will start to be located at the value given by 2000 in hex. Okay, and like I said, this can be done to locate your code at a specific spot in memory. Again, you'll see an example of that done in the lab, or it can be done if you want to store a variable at a specific spot in memory. While we're on the topic of allocating memory, let's talk about some directives that are specific to memory allocation. Okay, so this is kind of similar to declarations in variable declarations in C, or variable initialization. So a .skip command can be used and we would put .skip and the number of bytes after the command, and that would specify the number of bytes in memory to skip over. So this is a way of allocating memory or reserving memory, but not initializing it, not putting any specific value in that memory. So reserve uninitialized data space. Okay, if we want to initialize the memory, and specifically a byte of memory, we can use the .byte directive, specify the value that we want to put in each byte, and we can allocate a value to a byte or 8 bits of memory space. And of course we can allocate different amounts of memory space to our data. .half for half of a word, 16 bits. We are a 32-bit processor in the case of the NIAS2, so we have 32-bit words, and as such, .word to allocate 32 bits of memory, or a variable to a 32-bit memory space. We can use .ascii to allocate 8 bits of memory per ASCII character. We'll come back to address ASCII and what ASCII is a little bit later in the course. And we can use ASCII Z directive to allocate 8 bits per character, but additionally we have, and this is what differentiates ASCII Z from ASCII, it ends with a trailing null character being zero, a value of 0 in that final byte.